Welcome to Lecture 8 of Foundations of Artificial Intelligence. Today we're going to be learning about other ways to represent knowledge in artificial intelligence. Specifically today we're going to cover semantic networks and frames. In our last 4 lectures we covered the topic of logic, examining both representation and reasoning from the perspective of propositional logic and then first-order logic. In today's lecture we're going to start by taking another look at knowledge representations from a broader perspective. Then we'll move on to semantic networks. We'll discuss and/or trees, is-part hierarchies, general networks, interpretation, inheritance, and inference in semantic networks, and lastly, some biomedical examples of semantic networks. Next, we'll move on to the related topic of frames. We'll see how they're different from semantic networks. Here we'll learn about slots, default values, inheritance and inference in the context of frames, and again, some biomedical examples. Then we'll touch briefly on the topic of scripts and see how they're different from frames. And lastly, we'll examine some other semantic network related representations that will give you a broader context of what's available out there. In some of our previous lectures on logic, we learned about different representations specific to logic, and we also learned a little bit about how knowledge could be formatted into a knowledge base from which we can derive conclusions. Years of research in knowledge representation suggests that intelligent systems require a large amount of real-world knowledge to achieve anything useful. Think about how human beings go about tackling real-world problems. They have to use their own knowledge resources, including their experience, training, and other external resources they might have available, such as the internet or books. Let's quickly review some of the ideal characteristics of a representation or a knowledge base. They should be interpretable by humans. We should be able to encode information in a knowledge base without significant effort. Also, there should be some way for users to understand what the system knows and how it's drawing conclusions. In other words, we want our knowledge base to be transparent and not some kind of black box. And importantly, both the knowledge representation scheme and the reasoning methods that are chosen to work together have to be compatible. For example, a knowledge representation strategy designed for logic won't necessarily work with a reasoning strategy designed for a different kind of representation, like the ones we're going to learn about today. Here's a figure we saw in our first lecture, describing some of the major knowledge representation techniques used in artificial intelligence. At this point, we've covered representation in 2 forms of logic. Today, we're going to cover semantic networks and frame representations. And later, we're going to cover production rules. As we'll learn later, production rules are something that are used with rule-based systems, which are a popular foundation for expert systems, again, which we'll learn more about later. Let's briefly take a big picture look at these different representations in AI. Logical representation, which we've already covered, is generally seen as less efficient when we want to make a restricted class of inferences. Using these representations, it's often difficult to represent common sense, time, beliefs, or uncertainty. Up to this point, everything we learned in logic has to do with certain conclusions about truth or falsehood. Of note, there are special logics, such as temporal and modal logics, that allow this kind of representation. However, reasoning with these systems is still often inefficient. Today, of course, we're covering semantic networks and frames, which are also referred to as structured objects. These offer a simpler and more natural set of representations, and they don't require formal specification of semantics. They can be used to represent factual knowledge about classes of objects and their properties. Ultimately, they offer a declarative, static representation of facts and relationships. A quick preview of rules and rule-based systems. This representation relies on if-then expressions. As a result, rules have a connection to what we've learned about with logical implications, which also represent an if-then relationship. However, in rule-based systems, there's more emphasis on what is done with the rules rather than what they mean. Often, such systems are used to make decisions about what to do next, rather than just to describe relationships between individuals. So we just introduced the term structured objects. This term is in contrast with production rules and formal logic. Structured objects refers to a knowledge representation formalism whose components are essentially similar to the nodes and arcs found in basic graphs and networks. Basically, this is an attempt to incorporate the desirable features of human memory organization into a knowledge representation. specifically that of making associations between objects. As alluded, structured objects include semantic networks, also sometimes just referred to as nets, frames, as well as object-oriented programming, which is actually an idea derived from frames, and other similar representations such as scripts. So now let's dive into semantic networks. Semantic networks are also known as association networks. And basically, semantic networks are labeled directed graphs. Here, each node represents a proposition from logic. This is basically an object that captures an individual, a concept, or an event. Each arc, or link, represents a specific relationship between two objects. One of the largest contributors to the popularity of semantic networks is that you can easily represent them graphically. Here's an example of just a generic network. There's not a lot of meaning that can be derived from this, other than that there are connections between cities. This fits the definition of a network in general. We have nodes and arcs, or edges. Here's an example of a semantic network. One of the most glaring differences between the two examples is that in semantic networks, we have the arcs specifically define some kind of relationship between the two node objects. For example, Bill is the husband of Anne, and Anne is the wife of Bill. Or Tom is the father of John. For historical context, semantic networks were developed by Quillian in 1968. They were originally designed as a model for human memory and called semantic memory. If you're interested, here's the original paper. Next, let's go through some other semantic network concepts. We'll start talking about the lexical part, or the names of the different parts of a network. Again, we have nodes, which denote objects, individuals, or classes. An example is represented here as water. Then we have links, also known as edges or arcs. Here's one that ties fish and water together with lives in. In other words, fish lives in water. And then we have labels. Labels are just the text that define the node or the edge. Next, let's talk about the structural parts of a semantic network. Links and nodes form what's known as a directed graph. In other words, there's a directionality between the links. In this case, animal is not a mammal, but mammal is an animal. If it were true both directions, we'd have to have arrows or directions that point both ways in the network. And not surprisingly, the labels are placed on links and nodes. Next, we get to the semantic part of a semantic network. Here, meanings are associated with the link and node labels, and the details of the underlying meaning of the text will depend on the application domain. Next, let's examine the procedural parts. This refers to the mechanisms we use to build or examine a semantic network. The term constructor describes a part that allows the creation of new links and nodes. Destructors allow the deletion of links and nodes. Writers allow the creation and alteration of labels, and readers can extract answers to questions, usually using some form of inheritance. At the end of the day, when it comes to semantic networks, there's plenty of flexibility in terms of how these representations can be created, and as we'll see later, this has both advantages and disadvantages. Here's another example of a semantic network. We've already talked about nodes and edges, where edges describe relationships between nodes. As mentioned, nodes can represent concepts or individuals. For example, by concept, we have the concept of animal, which is basically a general category. Same thing with mammals. Individuals represent specific entities or unique values. For example, mammals has the relationship legs with the number 4, which is considered to be an individual. Or we have a specific animal, in this case, Bill, who is a member of the concept cats. One particularly simple form of semantic network is known as and/or trees. Here's an example of what one looks like. Here we can follow the flow from the bottom to the top in terms of decision making. This tree captures the idea of when are we able to eat. You might recognize the structure of an and/or graph from our earlier discussion of forward and backwards chaining in logic. Here there are two node types, and, given with a branch with an arc between it, and or, given by a branch with no arc. Given that distinction, let's try and interpret this simple and/or tree. We're able to eat if any of these three is satisfied, since they're all connected as an or. In order to eat, we can earn money, steal food, or borrow money. To determine if we can eat, we might need to check and see if it's true that we've earned money. In this case, in order to determine if you've earned money, you'll need to know if you've written a book or if you found a job. Either can be true to say that you've earned money. To determine if you've found a job, you'd need to know both whether you've consulted an agency and whether you've prepared a CV. Notice the and symbol here. We can interpret the right side of this tree similarly. Now let's examine another simple form of semantic network called an is-a hierarchy. An example of this would be a taxonomy. From the perspective of set theory, is-a corresponds to the set and subset relationship. Notice that as we go up the tree, there is an is-a relationship connecting each node. In other words, a German Shepherd is a dog, which is a pet, which is an animal, which is a living thing. If we want to refer to something that's below or more specific in the tree, we can say that the thing that's more general is a class, and the thing that's more specific is a subclass. Differently, if we're looking at this object, plant, and we're calling that the class, then the more general class above it can be referred to as a superclass. Specific items, found at the bottom of the tree, can be referred to as an instance of something higher in the tree than itself. In other words, a poodle is an instance of a dog. This terminology is reserved for individuals rather than categories. We can also take these kind of hierarchies all the way down to the molecular or atomic level. At the end of the day, it's always best to limit the representation we're using depending on what it is we want to represent and how we want to manipulate the knowledge in that representation. Here's an example of an is-part hierarchy. In this case, we're trying to represent anatomical groupings. So here we have dog at the top, and all these items below it in the tree are a slightly more specific part of the dog, such as the head, the body, appendages, and tail. Any of these could be further subdivided if needed. For instance, head has the parts ears, nose, eyes, and mouth. In semantic networks, we can actually conduct some simple forms of inference. In particular, inheritance is one of the main kinds of reasoning used by semantic networks. Let's first reiterate that the is-a relation is often used to link a class and its superclass. In this example, we know that cat is a mammal. We also know that mammals have a vertebrae. We can infer that a cat has a vertebrae because a cat inherits the property of its more general superclass. Similarly, some links, such as has part or is part, are also inherited along is-a paths. Here's another semantic network where we have two specific birds at the bottom named Rusty and Red. They're both robins. A robin is a bird, and a bird is an animal. In this case, both Rusty, Red, and Robin all can inherit has part wings because the more general term bird in this network has the part wings. Again, notably, the semantics or the meanings behind a semantic net can be relatively informally defined, or they can be very formally defined based on the developer. As such, the formality of the semantics is often defined at the implementation level. So ultimately, it's up to the person who's putting together the semantic network to determine how formally the semantics need to be defined. Let's talk about some other general properties of semantic networks. First off, any arc defines a binary relationship which holds between objects, where these objects are denoted by nodes. These binary relationships are the easiest to represent. Looking at the semantic network, we can turn every edge between two nodes into a corresponding predicate like we had from first-order logic. For example, this part of the network can be captured by mother, John, Sue, which means that John's mother is Sue. Or this part of the graph can be represented by this expression, John's age is 5, and so on. You can also have other relations beyond just the is-a or is-part. For example, you can have cause. This expresses a causal relationship. For example, fire causes smoke. We can further go on to define different archetypes in semantic networks. The first describes a relationship between an individual and a concept. We call these members. For example, X is a Y, and X is an instance of Y. As a specific example, the individual opus is a member of the group Penguin. Another archetype describes a connection between a concept and another concept. This is referred to as a subset. In other words, X is a kind of Y. Or in our specific example, penguin is a subset of bird. Lastly, we can have a relationship between two individuals. This is referred to as an R relation. Or X has a specific relationship to Y. In other words, our penguin Opus is a friend of Bill, and Lou is a parent of Ian. In our example below, the relationship between the individual Novak and the category Bachelor would be an example of a membership arc. The relationship between the category Bachelor and the category Student is an example of a subset arc. And in this case, the individual Novak being enrolled to the individual class type Mathematics is an R-relation arc. So far, we've just examined arcs that capture a binary relationship between two objects. But what about non-binary relations? To represent a non-binary relationship in a semantic network, we need to do something called reification. This is where non-binary relationships can be represented by turning the relationship into an object itself. The term reify means to consider an abstract concept to be real. Here's an example where we have the relationship give. However, this relationship involves three things, or three objects. You have the giver, John, a recipient, Mary, and the object being given, in this case, a book. Here's another example with the relationship brings. In this example, we have the bringer, or who. We have the location to which it was brought, the where, and the object brought, or what. However, semantic networks aren't always completely straightforward. Let's explore the issue of multiple inheritance. In a semantic network, a node can have any number of superclasses that contain it. Below we have this example with an individual Nixon being an instance of the category Republican as well as an instance of the category Quaker. However, when we define a semantic network that can inherit objects from any of its parent nodes or superclasses, situations can come up where we have conflicting inheritance. For example, imagine we have the category Republican with the characteristic pacifist being generally no. But on the left, we have the category Quaker, which generally has the value of pacifist yes. Knowing only the information in this semantic network, how would we determine whether Nixon was a pacifist or not? Here's a more compact way of illustrating this situation. Depending on the semantic network you're working with, they might handle this multiple inheritance problem differently. In other words, the specific strategy that semantic network uses to determine which values a specific object will inherit. The simplest approach is that all possible values will be inherited. However, this can lead to conflicts like we just saw. Another simpler approach that can work in a lot of situations is that only the most specific value or values are inherited. Yet another strategy is that default values of relationships can be assigned at every level in the hierarchy. For example, in this semantic network down here, we have baseball player is a man is a person, where a person has a nose, and we've set the default value for a person's height to be 163 centimeters. However, the default value for a man's height is set to 178 centimeters. And lastly, for the more specific category baseball player, we might set the default height to 195 centimeters. Using these kind of default values can be more efficient than listing all the details in terms of everything that's inherited from every level. Overrides can also be specified. In other words, a more specific category can override the information received from a more general one. Let's imagine for a moment that baseball player doesn't have a default height. Based on what we've learned so far, baseball player would inherit the properties under the most general term it's connected to. In this case, height being 163 centimeters. However, we could set up our semantic network to have a default where the more specific value, in this case a man's height of 178 centimeters, is inherited instead. Imagine for a moment that we had a much more complex semantic network in front of us. And imagine that we wanted to understand how two objects in the network were related to one another. For this, we could use what's called an intersection search. It's one of the earliest ways that semantic networks were used. Here, we want to find the relationship between objects, and we do so by spreading what's called the activation from each of two nodes and seeing where the activations meet. For example, let's say we have the question, what is the relationship between Chicago Cubs and Brooklyn Dodgers? To get the answer, they're both teams of baseball players, let's check out an associated semantic network. Essentially, what an intersection search does is, starting with the two terms in question, in this case the Chicago Cubs and the Brooklyn Dodgers, we activate or step through the network until we reach a node where they meet. In this case, from Chicago Cubs, we're connected to Three Finger Brown, which is connected to pitcher, which is connected to baseball player. And from Brooklyn Dodgers, we're connected to Pee Wee Reese, which is connected to fielder, which is connected to baseball player. So we can use this intersection search to find a node that represents the relationship between our two starting objects. Now let's revisit this idea of more complex semantic networks, and we'll bring up the term tangled hierarchies. These are hierarchies that are not simple trees. These pave the way for another type of inheritance conflict than the one we'd already seen in our Nixon example. So here's our starting semantic network. We have an individual Oliver, which is an instance of both category ostrich and category pet bird. Oliver is also an instance of the broader category bird. Similarly, an ostrich is connected to bird, and pet bird is connected to bird. On the left we have ostrich, which cannot fly. But up at the top we have a bird which generally can fly. So now our question is, can Oliver fly? Well, if Oliver inherits everything, obviously we get a conflict, where we think Oliver both flies and doesn't fly. One way to handle this is to give Oliver the property no flies. However, that means that every instance of ostrich has to also have the property no flies attached to it. So if there were other individuals other than Oliver that were ostriches, they'd each individually have to have flies no. To get around this, we could design an algorithm that more intelligently traverses what gets inherited by an object. Such an algorithm will ensure that specific knowledge always dominates over general knowledge, without having to individually annotate all instances of ostrich in this example. So how do we do this? Well, to understand how this is done, first we need to understand what's called inferential distance. Let's check out this elephant example on the bottom. We have Clyde, an individual elephant. Clyde is an instance of the category circus elephant, which is an instance of the category royal elephant, which is an instance of the category elephant. And finally, elephant has the property is the color gray. However, royal elephants are not gray, represented by this line with slashes through it. The ends on the left represent the levels of this hierarchy. In this example, if we assume that Clyde inherits everything above it, Clyde will be defined as both gray and not gray at the same time, which of course is a conflict. We can try and resolve inheritance through simple distance first. In other words, the shortest path between Clyde and the property gray. In this case, Clyde is most closely connected to elephant, which would then inherit the color gray. This would be incorrect in this situation. Instead, let's try inferential distance. To apply inferential distance, we need to focus on the longest inference path. So in this case, getting from Clyde to either royal elephant or elephant must go through the longest path possible. Because we're looking for the longest path, we're going to ignore this connection between Clyde and elephant, and we're always going to go through this longer path if we're going to go from Clyde to elephant. So now in determining the inferential distance, we either have an option of 1-2 steps to get to royal elephant, or 1-2-3 steps to get to elephant. Using inferential distance ignores redundant links that are shorter. Lastly, our inheritance is determined by which nodes are closer based on inferential distance. In this case, Clyde is closer to royal elephant than it is to elephant, based on the inferential distance. Therefore, Clyde inherits the not gray property of royal elephant, but not the gray property of elephant. Unfortunately, there's still a problem with using inferential distance. Specifically, it only defines a partial ordering involving a set of common nodes. So it won't be any help with our previous Nixon example. Again, the reason is because from Nixon we have two separate inheritance paths, rather than a single one with different distances to consider. Here we can see the Nixon example illustrated similarly to the elephant problem from the last slide. In general, an inference engine, or the algorithm built into a semantic network to decide how inheritance works, will be composed of many procedural rules like using inferential distance in order to define how the semantic network should be processed. These rules must be clearly specified in order to preserve the desired meaning or to make correct inferences. Now let's review some of the advantages of semantic networks. When it comes to interpretation, they're easy to visualize, any related knowledge is easily clustered, and the semantics or real-world meanings are clearly identifiable from the labels. When it comes to representation, semantic networks are flexible and general, where the relationships can be arbitrarily defined by whoever's putting together that semantic network. In other words, a knowledge engineer. Also, in some cases, formal definitions of semantic networks have been developed. Additionally, formal definitions of semantic networks have been developed. They're efficient in space requirements, objects are only represented once, and they can be used to represent events and natural language sentences. Lastly, when it comes to inference, this process is basically reduced to a search of the network itself. So there's no need for proofs like there was in logic. But now let's look at the disadvantages of semantic networks. First, having this kind of general representation can be a problem unless we're clear about both the syntax and semantics in each case, or in other words, each semantic network we develop. There aren't really any formal standards about node and arc values. So in other words, the semantics of semantic networks aren't really strictly defined. They also have a limited expressiveness, which means they may require a number of specially coded procedures in order to handle certain situations. In other words, there's no way to express non-monotonous knowledge like you can in first-order logic. In non-monotonous knowledge, it's possible to change the truthfulness of something once more information is added. There's also no easy way to express n-ary relationships. However, the process of reification, which we touched on, could be utilized but can add its own complexities. Next, inference in semantic networks can cause problems also, specifically when you have inheritance from multiple sources and when exceptions in inheritance are required. Further, any facts that are placed inappropriately, for instance by accident, can cause some serious problems in the inference process. These above problems make it difficult to verify and validate the functioning of semantic network systems, to share knowledge, or to reuse knowledge, in other words, build off of an existing semantic network, and similarly, to acquire knowledge methodically, in other words, to expand or adapt that network slowly over time. Let's go through a quick example of constructing a semantic network from the ground up. Let's walk through this using the example of the story of Othello. First off, Othello was a general who was married to Desdemona. Iago was a captain who was married to Emilia, and he hated Othello. Iago told Othello lies about Desdemona, and Othello killed Desdemona with a pillow. He felt remorse and killed himself with a dagger. So let's start with our first statement. Othello was a general who was married to Desdemona. Here we have the objects Othello, general, and Desdemona, and we can see the appropriate relationships laid out. Next we'll add Iago was a captain who was married to Emilia. He hated Othello. Here's the new part, where we've added the objects Iago, Emilia, and captain. Iago is married to Emilia, Iago has the rank of captain, and Iago hated Othello. Next we have the sentence Iago told Othello lies about Desdemona. Here we have the action lying, which involves connections between three objects. So here we have to reify. That means our relationship lying is now an object. Here the liar is Iago, and he deceived Othello about Desdemona. Lastly, we add the sentence, Othello killed Desdemona with a pillow. He felt remorse and killed himself with a dagger. Here are the new parts. We see again that we need to use reification in order to add the relationship killing twice. In our first killing, we have the killer Othello, who killed Desdemona. The weapon used was a pillow, and the motive was jealousy. The second reification using killing, we have a weapon dagger, a motive remorse, and both the killer and the killed are the same person, Othello, because he committed suicide. Now that we've built this network, let's look at a brief example of how we might conduct a simple inference search. Let's say we have the question, what do the pillow and the dagger have in common? We can use this idea of spreading activation to see where those two ideas connect on this network. So we start with the two items in our question, pillow and dagger. The yellow numbers throughout show the activation steps as we move from our original starting points and look for an intersection. So here we have dagger moving to killing as number 2, which then connects to remorse, number 3, or Othello, number 3. Over here from pillow, it connects to killing, number 2, which connects to jealousy, Desdemona, and Othello. At this point, our connection occurs at Othello, and we can draw the conclusion that the dagger and the pillow are weapons used by Othello in the killings. Now let's look at a simple biomedical example of a semantic network. We can see a number of the relationships we've already talked about on edges of this network, such as is a, has, and causes. At the center of this network is a medical problem. Sign or symptom is a subclass of that medical problem because it is a medical problem. Over on the left we have a drug, which is a subclass of treatment. And there's a connection between treatment and medical problems that could either be treats, causes, prevents, or complicates, depending on the context. Again, because of the flexibility of semantic networks, the engineer of this network could have done it in a number of ways. Here's a slightly more complex example of a semantic network looking at lung cancer. Here at the center we have lung cancer, which is a part of the more general group cancer, which is further a part of the more general group disease. Over here we have treatments, with different kinds of treatments being subclasses of the group treatment. Going further down the tree, we can see different subgroups of lung cancer. For instance, lung cancer is next divided into the more specific categories mesothelioma and primary lung cancer. Primary lung cancer can be further broken down into non-small cell lung cancer and small cell lung cancer. And lastly, non-small cell lung cancer can be further broken down into squamous cell carcinoma, large cell carcinoma, and adenocarcinoma. The ULMS, or Unified Medical Language System, is another practical example of a semantic network in the medical field. This is basically a medical terminology system consisting of a set of broad subject categories, or semantic types, that provide a consistent categorization of all concepts represented in the UMLS metathesaurus. It also includes a set of useful and important relationships, or semantic relations, that exist between semantic types. The major groupings in the UMLS include organism, anatomical structure, biological function, chemical, physical object, and idea or concept. There are also 5 major categories of non-hierarchical relationships in the UMLS. These include physically, spatially, temporally, functionally, and conceptually related to. Here's a link for the ULMS if you want to check it out more. Further, here's a high-level illustration of the ULMS semantic network. In this particular illustration, edges without an arrow represent is-a links, where items higher up in the figure are more general. Edges with an arrow represent non-is-a relations, such as location of, process of, or part of. In this figure, we can also see some of the major categories defined by the ULMS mentioned in the last slide, including organism, anatomical structure, and biologic function. Note that each of these has a series of is-a links below it. If you're interested, there's also a number of ways to visualize semantic networks that have been constructed. Here's one example of a tool that allows you to do this, called VisuWords. If you want to check it out, here's the link below. Now let's segue from semantic networks to frames. As semantic network representations become increasingly complex in order to support a larger range of problem-solving tasks, the information in those networks also becomes more distributed and harder to access or visualize. This is where it becomes necessary to assign more structure to nodes as well as links. Also, there could be cases where we need node labels that can be computed rather than fixed in advance. The concept of frames adopt database ideas to help keep track and organize everything. The specific distinction between semantic networks and frames can be blurred in modern applications as they're closely related. But in general, frames generally have more structure than a semantic network. So now let's move on to frames. A little historical background: the concept of frames was originally devised by Marvin Minsky in 1974. Here's the original paper if you want to check it out. As mentioned, frames are basically a variant of semantic networks. They've also become a popular way to represent facts in expert systems. The inspiration for their development came from the observation that things of a given type participate in the same set of relationships. So in a nutshell, the goal of frames is to represent stereotypical situations. In other words, the essence of this form of knowledge representation is typicality with exceptions rather than just giving definitions. Ultimately, a frame is a knowledge representation formalism based on the idea of a frame of reference. First off, all information in frames relevant to a particular concept is stored in a single complex entity called a frame. Frames ultimately look like a record or a data structure. However, ultimately frames support inheritance like semantic networks do. A complete frame-based representation will consist of a whole hierarchy or network of frames connected together by appropriate links and pointers. At the end of the day, you can think of them as a form of object-oriented programming for artificial intelligence and expert systems. Here's a simple example of a frame representation. Every one of these boxes is a frame itself, where each frame has a variety of bits of information in it. Additionally, parts of a frame can be connected to other frames. Let's hone in on one as an example. In this case, hotel chair. The superclass of hotel chair is chair. Additionally, the hotel chair is given a default range of heights from 20 to 40 centimeters. A hotel chair also has the property of having 4 legs and a use of sitting. We can see how this frame captures what might be a whole grouping of relationships in a semantic network. Let's review some basic frame types. The first is a class frame. So here we have the class mammal, which is a subclass of the class animal. Additionally, mammal has part head. And of course, there could be more information included in this frame. Here's another example of a class frame. This one is class elephant, with subclass mammal, color gray, and size large. We can also have frames for individuals or instances. In this case, we have a specific individual elephant called Nellie. Nellie is an instance of the more general category or class elephant. And in this case, Nellie likes apples. Now let's define the term slots. Frames consist of a selection of slots that can be filled by what are called facets or fillers. The information in slots can be values, in other words, static knowledge, which might represent a default value or an exception. Slots can also include procedural attachments, otherwise known as daemons. Daemons can activate a rule if a value exceeds some threshold. In other words, this gives us a way to create dynamic knowledge. Maybe something's calculated on the fly. Slots can also have pointers to other frames. These pointers represent the inheritance hierarchy, similar to connections in a semantic network. Here we show a frame again and the individual slots that make up a frame. This frame is focused on hotel room. In this case, the slots include is a room, location being in a hotel, and contains. Here, contains has pointers to other frames in the frame representation, such as hotel chair. In this case, we've conveniently taken the relationship contains and connected our object hotel room to all the other objects which it contains. In most cases, slots are initialized with some kind of default value. For example, the location of a hotel chair in this case has the default value of hotel room. However, you could reasonably imagine that there might be situations in which a hotel chair is found outside a hotel room. It's also worth noting that it's easy to convert a semantic network into a frame, but maybe not vice versa. For example, it's easy to construct frames for each node of a semantic network by reading off its links. Here we have our baseball player semantic network example from earlier. We can see here how some of the objects from our semantic network can be converted to frame in our frame representation. For example, the object baseball player is converted to a frame down here. In this situation, imagine there's another object which baseball player is, specifically an adult male. Here, baseball player grabs the average default batting average for the player and adds it as a slot within the frame. Beyond the information that's in our semantic network, we can build this baseball player out frame further. Thinking about the potential of frames, they can be both very simple and get rather complex. The simplest type of frame is just a data structure with similar properties and possibilities for knowledge representation as a semantic network. It also has the same idea of how inheritance works and adopts the idea of default values. However, frames can become much more powerful when now you start using slots that contain instructions or procedures, also known as daemons. We use these to compute things from information in other slots or in other frames. Further, it's useful to know that slots in a frame can contain one or more facets. Facets can take on the following forms, including values, default values, ranges, in other words, what kinds of information can appear in that slot. If added specifies an action to be taken when a value in the slot is added or modified. This allows data-driven, event-driven, or bottom-up reasoning. Facets can also include if needed, another procedural attachment. This triggers a procedure which goes out to get the information that the slot doesn't currently have. This is an example of expectation-driven or top-down reasoning. Facets can also take many other forms, speaking to the versatility of this representation. They can include other frames, rules, semantic networks themselves, or other types of knowledge. It's useful to think of slots as fully fledged objects. Generally in slots, the main filler properties we want to represent include details about whether the slot is single or multi-valued, constraints on the ranges of values or typical values, simple default values for that attribute, rules for inheriting values for the attribute, rules for computing values separately from inheritance, the classes and frames to which it can be attached, and inverse attributes. In order to do all of this, the frame system interpreter must know how to interpret such frames. Another connection to our previous lectures on logic, it's useful to note that many parts of a frame can be converted back to propositional logic also. For instance, for all x, if x is a mammal, then x has part head. This is captured here by the frame for mammal, where anything that is a mammal also has part head. Or, for all x, if x is an elephant, x is a mammal. This corresponds to what we see here in this frame with elephant, where all elephants are a subclass of mammal. In this frame, we also have an individual Clyde. Clyde is an instance of category elephant. Based on the rules of inheritance for frames, knowing that Clyde is an elephant means that we can also conclude that Clyde is a mammal. And since we know that, we can also conclude that Clyde has a head. A quick side note about default values in frames, we can use this star symbol to denote defaults that can be overridden by an instance or a subclass. For example, the default value for mammals is that they're furry. However, the subclass of mammal, elephant, is typically not furry and has the default value of not furry. Usually, objects and classes inherit the default or typical properties of a parent class unless they have an individual property that conflicts with the inherited one. Another example is that Nellie is small, despite the fact that it inherits large from its parent class, elephant. Let's talk a little bit more about inheritance in frames. The inheritance of frames is similar to that in semantic networks. The idea of frame hierarchies is very similar to the idea of class hierarchies found in object-oriented programming, such as programming languages like Python. As in semantic networks, you can also have situations of multiple inheritance when using frames. In other words, more than one parent class can be allowed. It's important in these situations to specify the precedence order for parent classes. For example, Clyde is both an instance of a circus animal and an elephant, represented by these frames on the left. Here we have multiple inheritance of size, leading to a conflict in value between large and small. So within Clyde, we might need to specify the precedence order to disambiguate how we decide on size. However, this is not always sufficient. For example, in the situation of Clyde, imagine we want to inherit the size from elephant, but the habitat from circus animal. One way to achieve this is to specify a class in a frame called circus elephant and just define it there. Now let's briefly look at some terminology associated with building and using frames. First, we need to manipulate instances and classes. A class constructor makes a frame that has one direct superclass. An instance constructor makes instance frames. In this case, we have an input that's the name of the class to which the instance belongs, and the new instance is connected to that class by an isA slot. Then there's a slot writer. This installs slot values. The input of the slot writer is the name of the frame, the name of the slot, and the value. Lastly, there's a slot reader, which receives slot values. The input of the slot reader is a frame name, a slot name, and the output corresponding value. Stepping back, we can classify frames by their application. A situational frame contains knowledge about what to expect in a given situation. An action frame contains slots that specify the actions to be performed in a given situation. A combination of situational and action frames can be used to describe cause and effect relationships in the form of causal knowledge frames. In general, frames are good for representing class hierarchies, to model domains where objects are well defined and the classification is clear-cut. In other words, frames are not terribly good at resolving ambiguity. So let's dive deeper into the advantages of frames. Well, first, they make programming a knowledge representation easier by grouping related knowledge. As such, frames can be easily implemented using object-oriented programming techniques. Frames are also fairly intuitive for many applications and non-developers or people with minimal computer science experience. The frame representation is similar to human knowledge organization, it's suitable for causal knowledge, and it's generally easier to understand than logic or rules. Frames are both highly expressive and flexible. It's easy to set up slots for new properties and relations, and it's easy to include default information as well as detect missing values. Also, unlike in semantic networks, facets allow non-monotonic reasoning. Inheritance in frames is also easily controlled, and frames are actually useful for simulating common sense knowledge, which is a very difficult area for computers to master. Now let's dive into some more disadvantages of frames. First, just as in semantic networks, there are no real standards for defining frame-based systems. In other words, the semantics are not universally defined. Frames offer more of a general methodology than a specific representation. For example, if we're making a frame for a classroom, it might look different if we're thinking about it from the context of a professor versus the context of a maintenance worker. Another problem with frames is that there's no real formal reasoning or inference mechanisms. For instance, we don't always want the properties of a class stereotype to be propagated to a subclass. Further, any alterations to existing slots can have unintended consequences in the subclasses it's connected to. Frames also cannot represent exceptions. By their very definition, frames represent typical objects. As a biomedical example of a frame-based system, we have the Foundational Model of Anatomy, or FMA. This was developed at the University of Washington, and a link to this resource is down at the bottom of the page. The FMA is an ontology of human anatomy. Specifically, it provides a sound, accurate, and consistent formal theory of human anatomy. In practice, it's an evolving, computer-based knowledge source for biomedical informaticians, and is concerned with the representation of classes or types and the relationships necessary for the symbolic representation of phenotypic structure of the human body in a form that's understandable to humans and is also navigatable, parsable, and interpretable by machine-based systems. Here's a quick look at what the frames within the FMA look like. Next, let's briefly take a look at something called scripts. Scripts were originally proposed by Schenck in 1977. Here's the original paper. Basically, scripts are time-ordered sequences of frames. They're a knowledge representation scheme describing a stereotypical sequence of events, as well as the goals and plans of the actors concerned. This is a form of what's called expectation-driven programming. Scripts allow inference about implicit cause and effect relationships when interpreting different situations. Attached to each frame of a script, there'll be several kinds of information, including how to use the frame, what one can expect to happen next, or what one should do next. Some can be about what to do if our expectations are not confirmed. They can also express what to do when one encounters a new situation. Here's a basic example of a script. In this case, we have an eat at restaurant script. We have props, including the restaurant, money, food, menu, tables, chairs, the roles taken on by hungry people, wait staff, and the cooks. The point of view taken on by the script is that of the hungry people. The time of occurrence is the time of operation of the restaurant, and the place of occurrence is the location of the restaurant. Here we can see how scripts lay out events. As we go through these events, we can see that other scripts can be called, each with their own sequence of events and properties. For example, first apply the enter restaurant script. Then, if wait to be seated sign or reservation, continue on with the rest of the script, otherwise stop. Then get the maitre d's attention script, then please be seated script, then order food script, and so on and so forth. Let's quickly review the elements of a script, starting with entry conditions. In other words, what are the descriptors of the world that must be true for the script to be called? This is similar to the if part of an if-then statement. Then we have the props. These are the objects that make up the content of the script. Then we have roles, what actions are performed by the participants in the script, and scenes, temporal decompositions of a script into meaningful episodes. Lastly, we have the results. What are the outcomes following termination of the script? Here's another example and a breakdown of these different elements. Feel free to take a look at this in more detail. Lastly, when talking about scripts, let's think about its relationship with natural language. Scripts are used to organize a knowledge base in terms of situations that are to be understood. Imagine we have the text, Jack went to a restaurant. He decided to order steak. He sat there and waited for a long time. Finally, he got angry and left. Imagine that's our knowledge base. From this, we might want to use a script to answer questions like, what was Jack waiting for? And why did he get angry? Scripts can be effective in limited domains, but they can be inflexible in more general ones. The last section of our lecture will briefly cover some other semantic network-related representations that might be of interest to you. First is the very basic idea of a concept map. This is just a diagram that suggests relationships between concepts. It's a much more general and simple idea than a semantic network. In other words, it's less formal. Here's an example of a concept map, and notice that some of the relationships are very complex and don't always follow a very specific set of semantic relationships. A concept map could be a starting point for creating a more formal semantic network. Next, we have the idea of a topic map. This is a standard for the representation and interchange of knowledge. The emphasis here is on the findability of information or resources. Topic maps are similar to concept maps. However, topic maps adhere to the standards of the International Organization for Standardization. As such, their definition is a bit more reliable and formal. A topic map represents information using topics, which can represent any concept from people, countries, and organizations to software modules, individual files, and events. Topic maps also use associations, which represent hypergraph relationships between topics. They also use occurrences, which represent information resources relevant to a particular topic. Here's a simple illustration of a topic map. Here we have topics connected by associations with these lines, occurrences represented with dotted lines, and specific resources we might be trying to find within this resource pool. Lastly, there's conceptual graphs. First, note that this is not the same as a concept map. Concept maps are much simpler. Conceptual graphs are another formalism of knowledge representation. Basically, they're a graph representation for logic based on the architecture of semantic networks. There are three main areas of study with respect to conceptual graphs: a graphical interface for first-order logic, a diagrammatic calculus of logic, and a graph-based knowledge representation and reasoning model. Conceptual graphs try and hug the properties of logic a little bit more closely, especially when it comes to inference. Inference in conceptual graphs can make use of several different forward chaining rules, including graph generalization, specialization, and equivalent changes. When you try and draw conclusions by querying in a conceptual graph, this is called projection. Here we look for a conceptual graph pattern in another conceptual graph, making use of the conceptual type hierarchy and the conceptual relations. Okay, here's a summary of the content we've covered in today's lecture. We began by examining semantic networks and learned how they're easy to implement and interpret, they're very flexible, and they have a very simple inference system that relies on inheritance. Then we turned to frames, which basically extended semantic networks based on the concept of typicality. Frames are more efficient and have a clear inference strategy. Frames are also the foundation for many real-world knowledge bases. However, neither semantic networks or frames have a standard well-defined semantics, and this can limit their applicability and cause problems for inference in different situations. Next, we briefly looked at scripts, which basically extend frames to time-ordered sequences of frames. And then we looked briefly at a handful of other semantic network-related representations. Here's today's quote: "I am instinctively a network infrastructure plumber." Just a reminder that assignment 2 is due soon. The specific date is on the syllabus. Again, I thank you for your attention, and I'll see you in the next lecture.